All right, guys. So today we're going to talk about 1D kinematics. All right. Now you can ask, what is kinematics? This is a scary word, right? It's physics. It's scary. So actually, physics isn't scary at all. It's a lot of fun, and we're going to have a lot of fun this school year. But kinematics itself is the physics of motion. Okay, so the physics of motion, what does that mean? That means like driving, right? When you drive your car, you're going to see my little doodles are always chaotic. Okay, so if you're driving your car and you're moving side to side, this is motion, right? Throwing something, you have a baseball, you throw it, this is also motion, right? Dropping something. These are all different motions that we see in our daily lives, right? And these little arrows that you see, we're going to learn how to draw them. They're called motion maps, and they just demonstrate the way that things are moving. So let's start off with motion maps themselves. So let's say, I'll leave that there, actually. Okay. So let's say that you're driving up to a Starbucks drive-thru, right? So you're going to go get your pumpkin spice. You're in your car. The window's over here, right? This is the little person that takes your order. So when you're driving up, you're going to start coming in pretty fast, right? So we're going to have some fast arrows just like this. And as you get closer to the window, you're going to have to start stopping, right? So you're going to slow down, slow down, slow down. Once you make it to the window, you're going to have to stop, right? So that you can take your order. So if you notice, when we were moving fast, the arrows were longer. When we were moving slow, the arrows were shorter. And in the entire motion, you see that they are shrinking until you get to a stop. That's a simple motion map, right? So then same thing goes if this person's done ordering, they're going to take off with their new Starbucks. Oops, sorry. Too long. They're going to take off with their new Starbucks pumpkin latte, and they're going to drive off. So you're going to see the arrows start getting longer. So this is slow, right? And this would be fast, which means that we're increasing in speed, right? So this was slowing down. This is speeding up. And that would be a simple motion map. We can do this also with something being dropped, and we can do this with anything. So our arrows are pretty much showing how fast we're moving, right? And a dot would just show that you're in the same position, so nothing changed. So then, what are different things that we think of when it comes to motion, right? What do you think of? Of when you hear motion, right? What are some things you think of when you hear motion? One of these would be maybe velocity or speed, right? Another one would possibly be moving, which would be position maybe. And the last one would be maybe a distance over here. Distance also with this one. Maybe acceleration. Right? These are all different things you can think of when you think of motion. Sorry. So, all of these things do describe motion. Velocity and speed, position and distance, and acceleration. Now, all of these things, some of them had two different names, right? And velocity and speed sound like pretty much the same thing, right? Like you're moving at a certain velocity in your car and your speedometer says something, right? It'll say the same speed that you're moving at. But these things are actually different because we have two categories. We have vectors and we have scalars. And you should have already touched on this either if you took Calc 1, AB, or if you took pre-calculus. You should have discussed at least a little bit of vectors. Okay, so now we have velocity and speed. So both of these measure how fast you're moving. But one of these would be a vector and one of these would be a scalar. The difference between a vector and a scalar is that a vector has a magnitude and a direction. Sorry for my misspellings. You'll see that I do that a lot. And then scalars have only a magnitude. Okay? So vectors have a magnitude and a direction, and scalars have only a magnitude. So your speed, your speedometer, when it comes to your speed in the car, right? It's only taking account how fast you're moving. Does your speedometer tell you if you're moving north, south, east, west? Well, sometimes it could if it has the fancy little dash that says the direction that you're moving in. But for the most part, every car will have a speedometer. Think about the non-virtual one, just the one that moves up and down, right? Our speedometer that looks like this with the little speeds, right? So for the speedometer, it only measures how fast you're moving. It'll say like meters per second. But it doesn't tell you north, south, east, or west. So that means it's just a magnitude. It's just a number, right? So our speed would categorize as a scalar, right? Then we have velocity. So now you're like, my velocity is just how fast I'm moving. Maybe that's what's going through your head right now. But your velocity actually does take into account what direction. So let's say you take 20 steps per second north. Right? 20 steps per second north would be your velocity. Your speed, however, would just be 20 steps. Does that make sense? So our speed only takes into account the number, the value of how far we're moving, the magnitude. And our velocity takes into account our speed, but it also gives it a direction, such as north, south, east, or west. So if you have the fancy speedometer with the little north, south, east, west in a nice little luxury vehicle, then that would actually give you the velocity and not actually the speed. So this would be our velocity. And this would categorize as, if you want to take a guess, it's going to be a vector, right? So now just measurements, right? Both velocity and speed are measured in meters per second. Okay? The only difference is one has a direction and one does not. Now, our position and distance, right? So you can say position and distance are the same thing. Well, distance, I can tell you I'm 20 meters. If I tell you I'm 20 meters away, does that tell you anything other than I'm 20 meters away from some form of reference point? No, right? So if I'm 20 meters away, I can be 20 meters up. So if this is one person and the other person is 20 meters away, they can be 20 over here or 20 over here, 20 over here, right? We have no idea where he is. But if I say I'm 20 meters away, or I say I'm 20 meters north, right? Then we know that I am exactly 20 meters above this person, right? So there is a difference between distance and displacement, or distance and position. We're going to get into displacement now, is because the distance is just how far you are. Your position will tell you how far you are relative to a reference point, such as this person right here. All right, so this would be our reference point. A reference point, so it would be 20 meters above. So with this, we have distance, position, right? So our distance, we just found out, is nothing more than how far we are. So if we know how far we are, but we don't know where it is relative, would you count that relative to the reference point? Sorry. Would you count that as a scalar or a vector? It would be a scalar, right? I'm sorry, I wrote that really ugly. Right? This would be a scalar. Now, our position, if we know that we're 20 meters north, right? The fact that it says north gives us a hint to tell us that this is also a vector. Now, you may have heard the word distance, right? And you also may have heard the word displacement. Now, a lot of the time you'll hear these words used interchangeably, but they actually mean two different things. A distance is just how far you traveled. So if I start at the supermarket, let's say this is a supermarket, and I want to get to my house, my distance would be how far I walked. It'd be this entire path. Now, my displacement would be from beginning to end, a straight line, right? It's the shortest path. So similar to when you do a triangle, when you work with a triangle and it's like Sally went 20 steps to Susie's house and then down to Thomas's house, right? How far did they move? You would always just do the shortest line, which would be the last side of the triangle. So the distance would be the yellow. This would be your distance, right? And your displacement would be your shortest path. So our displacement has a direction, right? We just know how far we walked in the distance. But our displacements, let's say this is southeast, right? So we moved southeast, but we moved our displacement was okay. So our displacement was southeast, but our actual distance we ended up moving up and then over, right? So our displacement, would you qualify this as a scalar or a vector? If you chose vector, you're correct, right? So our displacement, since it's the shortest path, we have to say from where we started to where we ended, we have to give it a direction. Okay? Now, all of these are going to be measured in meters. Right? Obviously, the vectors would have a direction and the scalars would not. Now, the last one we have left, acceleration. Some people say when you hit your brakes, you're decelerating. Right? And that when you're hitting the gas, you're accelerating. Right? Now, this is actually not true. In both of these cases, you are accelerating. The only difference is negative acceleration and positive acceleration. So in both of these, you are actually accelerating. The only thing that changes is the direction in which you accelerate. So I know it goes against what most of you guys have learned from driving and riding your bicycles and stuff, right? But when it comes to acceleration, this is actually just positive and negative. There's no such thing as accelerating and decelerating. So if we have a positive and a negative, what does that hint at for acceleration? This would mean that acceleration is a vector, right? So acceleration is a vector, and it's actually measured in meters per second squared. And there is no scalar version of this. Okay, we're going to go through more vectors and scalars in the future. But as of now, this is all that we're going to be working with, because this is everything for kinematics. If there's any questions on this, feel free to email me or message me on Remind. Okay, so when it comes to the motion, right? When it comes to motion, let's say that Susie, right, walks from her house 20 meters in the positive direction, right, to Sally's house, right? So this is Susie's house. This is Sally's house. I don't know how to spell Sally. That's an attempt. Okay. So we walked 20 meters to Sally's house. But Susie forgot something, so she had to walk 20 meters back. How can we graph this motion? First thing we would do is we'd make a graph, right? And we'd label it position over time. Okay, we have our 0. Now, we don't know if she was moving faster or slower. Let's say she moved at a constant pace. So first, let's start with that motion map we mentioned, right? She moved at a constant pace. So we're just going to keep moving at the same rate. She forgot something, and she instantly turned around and started moving back at the same pace. Since it was at the same pace, all of these arrows would be the same exact length. Okay? Now, let's graph that position. So she moved up 20 meters because she made it all the way to Sally's house at a constant pace, right? So she'd be moving at the same rate all the way up to 20 meters. We don't really know how much time passed, right? But we always assume that time goes forward. Now, when we come back down, right, all the way back, we moved at the same rate. So we're going to end up with the same slope. The only difference is that now we're moving negatively, right? So we moved up, that's positive, and then we moved back down. That's a negative direction. So this is going to be our origin line. When we move up from our origin, we're moving in the positive. When we move down from our origin, we're moving in the negative. Now, if she moved at a constant pace, right, we can make that also a graph. So let's do a velocity time graph. Oops, my bad. Right? This is our, in this one, this is not our origin. This is actually 0 meters per second. Okay? Time always moves forward. We haven't discovered time travel yet. So time, our scalar. So time is a scalar. Time, which is a scalar, is going to always be moving positive. There's no such thing as negative time. So now over here, our velocity was always constant. So it would be a straight line. Let's say she was moving at 2 meters per second, right? It was always a straight line. So if this is 2 meters per second, Sally was always moving at 2 meters per second. Now, what changes? Right? What actually changes is, Susie. Susie actually went negative after a while. So she started moving positively. Then when she switched, at this point right here, she now started moving 2 meters per second in the negative direction. So she went from moving positive 2 meters per second to moving negative 2 meters per second. Now, if you look over here, the graph of this line, okay, is actually just the slope of this line. Now, what does that mean? That means that our position graph and our velocity graph are always directly related, because the position, let's change the color, sorry. To get from our position to our velocity, we use our slope, right? Now, from velocity to position, if you ever remember from geometry, the opposite of a slope is actually the area under the curve. And when we get back to school, we're going to be discussing both of these, and we're going to see that the slope is actually the derivative and the area under the curve is actually the integral. So we're going to be working with these when we get back to school. Now, this trend continues. I did something. Okay. Now you're going to see that this trend continues. What's the area? What's the slope of the velocity graph? They're straight lines. So that would mean that the slope is 0. So our last graph, our acceleration graph, is actually going to have a slope of 0. Because the same way that we went from position to velocity by using the derivative or the slope, it's going to be the same thing for our velocity to acceleration. So we're actually going to go from velocity to acceleration the same way. And from acceleration to velocity, it would also be the area under. Now, the cool things about these graphs is that these trends continue no matter what. Whether speeding up, slowing down, any of these situations, we're going to have the same exact thing, right? Now, if I say that something is constantly speeding up, right? So if something is speeding up, think about a graph of something that's speeding up. Would it be a flat? Oh, that's not how you do a graph. Would it be a flat line? Would it be increasing at a constant rate, or would it be increasing exponentially? So a position for something speeding up would be exponential, but the velocity would be increasing constantly, and the acceleration would be a straight line because it would be a constant acceleration. So we have something speeding up, we have a position graph, velocity graph, and an acceleration graph. Just like this. Position graph would be exponential, velocity would be increasing, and acceleration would be constant. Now if I had something slowing down, right? If I had something slowing down, we would have a negative acceleration. Let me redraw this. We would have a negative acceleration. We'd have our velocity decreasing towards 0. And we would have a position that instead of being exponential would be a logarithmic because it's flattening out. It's slowing down. It's getting to a constant position. This would be our position graph. Because the position of graph of something that's not moving, right? our acceleration would be 0. Our velocity would be 0. And our position would be stagnant. And remember, if the velocity is 0 and we know that it's the slope of the position graph, and the position graph is a straight line, our velocity is 0. Now, knowing all of this, we can actually add some numbers into this. So let's go ahead and let's work with this. You guys should all have access to this graph. Okay. So using this graph, create a scenario and motion map and calculate the total displacement. So, a scenario. What's happening here? We're moving at 3 meters per second, and then we're speeding up to 9 meters per second. Let's come up with a story. You can come up with your own. Pause this video and come up with your own if you would like to, and then compare it to mine to see if everything follows. But for my story, I'm going to say we're going to keep Susie in the mix. So Susie wants some ice cream. She walks outside at 3 meters per second. Sees the truck and speeds up to 9 meters per second in 6 seconds to catch it. Okay, so this would be my story, right? Susie wanted some ice cream, and she's getting her ice cream. She's going to work for it, but she's going to get it. So, now let's do our motion map. Susie's going to start off at 3 meters per second, right? So this would be the same. And then she's going to start to speed up until she makes it to 9 meters per second. We can say that these are 9. Now, one thing my motion map is missing is an origin. I'm going to assume that she's starting in the origin. That's a little too high. It looks like the word above. Right? So I'm going to assume she started at the origin. This little bar that I wrote is just an origin. When you draw your origin, you're going to make pretty much a plus. This is going to stand for origin. And then you give a positive and a negative direction. That's all you have to do. There's no such thing as assuming in physics. We'll talk about that the first day of school, because assumptions can be wrong. Okay, so you can either make positive left or right. That's fully up to you. I'm going to go ahead and make positive right. I'm going to flip this to the bottom so that it doesn't interfere with the sentence on the top. So I'm going to make this my origin. I'm going to say she's moving in the positive, and that backwards would be negative. So this entire time we're above the axis, so we're above 0. That means we're moving positively. So Susie's moving positively, speeding up. So we got our scenario, we got our motion map. Now let's calculate the total displacement. So what do we have to remember? We have to remember from position to velocity to acceleration, it's slope. And from acceleration to velocity to position, it's the area under. I'm getting my velocity graph. That's what I'm given. And I'm looking for my displacement. That's position, right? So that means that I have to look for the area under. If I look at this shape, I can either make a trapezoid, or if you guys saw where I was going, I jumped to the way that I usually like to do it. You can do a trapezoid, or you can go ahead and turn this trapezoid into a triangle and a rectangle. Okay, so we got to find this area. Now, what do we know about the area of a triangle? We know the area of a triangle, oops, I'll zoom out, is half base times height. And then we know the area of a rectangle is base times height. So, from here to here, what's the change? How can we find that? That's going to be our height. We started at 3 and we made it to 9. So our height is going to be 9 minus 3, right? And our base is going to be the length from here to here of time, which is 6. So it's going to be half of 6 times 9 minus 3. 9 minus 3 is 6. All right, so it's going to be half 6 times 6. Okay? We can do first however you want. Half of 6 is 3. We get 3 times 6. 3 times 6 is 18. You don't have to follow those same exact steps. Math, you guys know already, can be done many different ways. So let's hold on to this. We'll keep it right there. Now let's do our our rectangle, sorry. Base times height. Our base is once again 6, because we're going from beginning to end of time. It's going to be 6. And our height is going to be from 0 minus 3. So it's going to be 3 minus 0, sorry. So we have 6 times 3. 6 times 3, once again, is 18. So that means that the area... Let me erase these squares so that you don't get confused later. So that means that the area of my triangle is 18, and the area of my rectangle is 18. So the area of the full shape, right, is the area of the triangle plus the area of the rectangle. I can zoom in, sorry. Which is 18 plus 18, which is 36. Sorry. 36. Okay? So we know that the area of this shape is 36. Now, 36 what? Penguins, toast, miles, meters, right? It's 36 meters. So that means that this is 36 meters. We have to always keep our units. Okay? So 36 meters. That would be our total displacement. Got it. Now all we're missing is the acceleration. How can we find our acceleration? We go back to this rule over here. We're going from velocity to acceleration. We got to figure out the slope. So let's figure out the slope. Slope is y2 minus y1 over x2 minus x1, right? Rise over run. So looking at our shape, our rise is from 3 to 9, right? So 9 minus 3 over, our time was 6, right? We can look at it again. 6 minus 0. So we can do 6 minus 0. So we're going to end up with 6 over 6. So that means that our slope is 1. 1 what? We got to keep our units. So what would be the unit for this? The unit for this would be 1 meter per second squared, because this is our acceleration. So now we were able to calculate our acceleration. So our position, our change in position was 36 meters, and our acceleration was 1 meter per second squared. And these were our final answers. So now mathematically we understand what's going on in the situation, at least hopefully. If you still have any questions, remember you could feel free to message me on Remind or shoot me an email. The fastest response will always be through Remind. Okay. So now we understand that. So let's make some formulas. This looks awfully familiar, doesn't it? Isn't this the same situation as above? Just now we have these nasty variables. That's fine. We're going to go ahead and we're going to make some formulas. So we're going to derive the kinematic equations. If you Google these, you're going to find that there's 5. But they're all just manipulations of each other, so we're going to use 2. Okay? So we're doing the same thing. We got to figure out the displacement. How can we figure out the displacement? The displacement we know we can find using position to velocity to acceleration. We slope. And then we know area under when moving backwards. Right? So, let's go ahead and let's do it. Let's find displacement first. Right? I chose displacement. You could have done acceleration. I just want to do the area under first because we practiced it like that the first time. So, same thing. I have either a trapezoid or I have a triangle rectangle. Let's go ahead. Our area of our triangle is half base times height. So we're going to keep our half. Our base is from 0 to t final. So t final minus 0. And then from initial to final of velocity would be our base, right? From here to here. Would be our height. This is v final. This is v initial. This is v final. Right? So then we're going to do v final minus v initial for our height. Now we can't really replace anything, so let's clean it up. We get half t final v final minus v initial. Okay? Now I'm just going to clean this up one more time, and I'm going to change it to half v final minus v initial, and I'm going to change this t final to time. Okay? Because that is the total time that passed. I'm going to hold on to it like this. As you can see, from this step to this step, I just reorganized, and then from this step to this step, I did the same thing. I reorganized again. Now, let's go ahead and let's do the area of our rectangle. Oh, sorry. I was thinking something else. Base times height, right? Our base is from 0 to t final. So t final minus 0. And then our height is from 0 to v initial. So this will be v initial minus 0. What does that give us? Let's clean it up a little bit. That's going to be t final times v initial. I'm going to clean it up one more time to reorganize it, and I'm going to say v initial times time. Now, if we put them together, the area of the whole shape is going to be the area of the triangle plus the area of the rectangle, and I'm going to end up with half v final minus v initial times time plus v initial t. Now, out of my own personal preference, because That's how you're going to find it mostly online. I'm going to flip these. I'm going to go V initial t plus half V final minus V initial. Oops. Yeah, V final minus V initial. T is your position. Okay, so that's how we're going to solve for our position. I'm often going to call it displacement, so you're going to see me put it D. Okay, this would be our equation, but we're going to give it a little edit, so just give me a second. Now, let's move on to our acceleration. Our acceleration. Now we know it's the slope. So our slope is y2 minus y1 over x2 minus x1, right? Our y2 is v initial minus 0. Oh, no, sorry. V final minus v initial, sorry. That would be our y's. And then our run would be time final minus time final minus 0. So that means that our acceleration is v final minus v initial over time. And this is another key equation. This equation is going to follow you throughout the entire year. Now, we're going to use this equation to edit this one a little bit, so you can see the same equation that you usually find online. Okay. So, I want to replace this v final minus v initial. Right? Where can I find that? I find it right here. And I can say that acceleration times time is equal to v final minus v initial. So I can replace v final minus v initial with at. So what I'm going to do is I'm going to turn this equation into displacement equals v initial t plus half at times t. If we replace this one more time, we're going to end up with displacement is v initial t plus half a t squared. This is one of the main kinematic equations, and if you were to Google it right now, this would 100% show up. So these two are actually the same equation. They're just manipulated using replacement of variables. Okay, so our top two kinematic equations, right? Our top two kinematic equations, and the only two we're really going to work with is the first one is d equals v naught t, or v initial t, plus half a t squared. V naught is equal to v initial. You'll see me swap them back and forth. And then acceleration is equal to v final minus v initial over time. So these are going to be the two main equations that are going to help you throughout this entire school year. And that is it for 1D kinematics. Go ahead and practice out the practice problems. I will be posting some solutions.